Hello everyone, welcome to Technogate. So now we will discuss the some of the problems of the merge sort algorithm. Okay, how merge sort works here. Okay, let's take one problem here. So it's a very good problem. So here, suppose there are four sorted list each of n by 2 elements each. Okay, so if we merge these lists into a single sorted list of 2n elements, how many key comparison how many key comparisons in the worst case using efficient algorithm. Okay, so let's check here. So 4n minus 3, B is 3n minus 1, C is 4n minus 1, and D is 2n minus 3 here. Okay, so now let's check here. So here, what is the first problem here? So here four sorted list of each n by 2 elements in. Okay, if we merge into the single sorted list of size 2n elements, we want 2n elements here. How many key comparisons in the worst case? Okay, so the worst case using efficient algorithm here. Okay, so here worst case, how many comparisons are there? So in the number of comparisons. Okay, so number of comparisons in the worst case in merge procedure, how much? Here m plus n minus 1 number of comparisons are there in the worst case. If one list contain m elements, okay, if one list contain m elements here and second list contain n elements here. So here how many element comparisons are there? M plus n minus 1 comparisons are there. Okay, so now here n by 2 element in each list, so what will happen here? So n by 2 here, n by 2 here, n by 2 here, n by 2 here. There are four shorter list of size n by 2 elements here. So here n by 2 plus n by 2 make one element here, one n element, and n by 2 one element here. So how much here? So number of comparisons. Okay, so for this list, how many number of comparisons are there? Here m, here m plus n minus 1 here. So n by 2 plus n by 2 minus 1. How many there are? N minus 1 comparisons. Okay, and how many elements are there here? N elements are there here. N elements are there. Okay, so n minus 1 comparison for this one. Here n minus 1 comparisons are there, and here again n by 2 plus n by 2 minus 1. So n minus 1 comparisons are there. N minus 1 comparisons are there here. Okay, so for this n by 2, n minus 1 comparison, again n plus n make here 2n elements here, so we want 2n elements here. Okay, 2n elements are there. So number of comparisons are what? So number of comparisons are how many here? So here number of comparisons are here n element are there, here n element are there. So m plus n minus 1 here. So n plus n minus 1 means 2n minus 1 comparisons are there. So total number of comparisons are 2n minus 1 for this list. So before n 2n minus 1, here n minus 1 comparisons are there for this list. For n minus 1 for this list, n minus for this list. Okay. So suppose is a numbering here first one, here second one, and here third one. Okay. For second list is, so here for first list, second list is, so here n by 2 here. So number of comparisons are n by 2 plus n by 2 minus 1. So again here n minus 1 comparison. So n minus 1 here, n minus 1 here, and 2 n minus 1 here. So total number of comparison, how many total number of comparisons are there here? So let's check here. So total number of comparisons are what? Okay. So total number of comparisons are how much here? Let's check. So here n minus 1 for this one, n minus 1 plus here n minus 1 plus 2n minus 1 comparisons are this one, 2n minus 1 here. So how much here? There are n plus n, 2n, 2n, 4n, and minus 3 number of 4n minus 3 comparisons. So how many are there? Are A is the correct answer. So A is the correct answer here. So it's a very good problem here. So here 4 shorted list. So here list is shorted. In the previous part there is unshorted. That's the reason we have to short the individual list here. But here no need to shorting here. Already shorted list are there. So here 4 minus 1, 4 minus 3, 4n minus 3 list. Clear? This one. So this is one of the good problem here. Let's check another one. So another one is next one is what? Merge sort uses. So this is one of the gate problem, 1 mark problem here. So merge sort usage. Okay. Option A, divide and conquer. B is backtracking. C is heuristic approach. D is greedy approach. Okay, this one. So here let's check here. So merge sort uses what? So merge sort is the application of divide and conquer. Merge sort is the application of divide and conquer. No need of backtracking here. No need of heuristic approach here. No greedy approach. So merge sort comes in the divide and conquer technology. Okay. So what are the applications of merge divide and conquer? You're finding maximum minimum in the given array. Find power of an element. Binary search. Merge sort is there. Quick sort we will discuss in the next upcoming lecture. Quick sort is a very important algorithm. Okay, kth maximum minimum element. Okay, iteration matrix multiplication. So merge sort is a very important algorithm, comes in the divide and conquer approach. Okay, so now next one let's check. So it's a very important algorithm, is a gate 1996 problem here. One of the gate problem, gate 1996. So what is the problem here? If someone uses straight two-way merge sort algorithm to sort the following element in the ascending order. Okay, so what are the elements here? They're 20, 47, 15, 8, 9, 4, 40, 30, 12, 17. Okay, then the order of these elements after second pass of the algorithm is. Okay, so after second pass of the algorithm, what will be the order of these elements here? So these are the options are given here. So what are the options are here? 8, 9, 15, 20, 47, 4, 12, 17, 30, 40. B is 8, 15, 20, 47, 4, 9, 30, 40, 12, 17, 15, 20, 47, 4, 8, 9, 12, 30, 40, 17. And D is 4, 8, 9, 15, 20, 47, 12, 17, 30, 40. Okay, so let's check here. So here is a two-way merge sorting. Two-way means elements are merged in two-way. Okay, means two element at a time. Okay, you remember this one is a two-way means two elements. So suppose this is one element here, one element here, then this is two element here. Two-way merge here. Okay, so here two elements are there. So merging in this way only. Okay, this one. Two element merge at a time. Okay, so these are the elements here. So in the after second pass of the algorithm, so second pass means okay, when we divide, then single elements becomes here until single elements remain here. After that we merge them. Okay, so merge will start. So second algorithm, so a one time algorithm will be finished when merge procedure will call. So algorithm is completed when the merge procedure is called. So how to merge the procedure called? Look here. So second pass of the algorithm. Which algorithm? Merge sort algorithm. So let's see how it works here. So here works here like so 20, 47, 15, 8, 9, 4, 40, 30, 12 and 17. Okay, these are the element. Okay, so divide this one. So 20, 47, 15, 8, 9 here. How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5 elements this side and 5 this side. 4, 40, 30, 12, 17 here. Here 20, 47, 15, 8, 9 here. 4, 40, 30, 12, 17. 20, 47 here. 15, 8, 9, 4, 40 here. 30 here. 12 here and 17 here. Okay, then here 20 here, 47, 15, 8, 9, 4, 40, 30, 12 and 17. Okay, this one. Then the single elements are there here. So we divide the elements until single elements becomes here. Now the first pass will be start. So when divide all the elements, the problem becomes small. After that, we uh, start the first pass here. Okay, so how would the first pass is start here? Let's see here. Okay, so these are the element here. These are the element here. So what are the element here? Like a 20, 47 after division, this one 15, 8, 9, 20, 47, 15, 8, 9, 4, 40, 30, 12 and 17 here. Okay, this one. So let's check here. So two element, one two, because it is a two-way merge sort. So two-way merge sort is there. Okay, two-way merge sort is there. So how it works here? Let's check here. So the first pass. Then what will happen here? 20, 47 shorted here. 8, 15 because merge procedure shorted sub array. 4, 9, 30, 40, 12, 17. So this is the first pass. So after first pass, this is the answer. After first pass is the answer. So here after second pass, what will be the answer here? After second pass, what will be the answer here? Let's check here. So again merge to both of them here. So this is the shorted sub array and this shorted sub array. So 8, 15, 20, 47 here. And this one again 4, 9, 30, 40 and 12, 17. This one. So this second pass. This is the second pass here. Okay, this one here. So 8, 15. So what are the order here? 8, 15, 20, 47. So 8, 15, 20, 47. So B is only in B, only option B. These are sequence only. So 8, 15, 20, 47, 4, 9, 30, 40, 12, 17. This is the answer. This is the answer. These are the B is the correct one. B is the correct one. Okay. So this is one of the gate problem here. Gate 1996 is a very good problem. So second pass means algorithm start when all elements single. Okay. After that the first pass start, second pass will start, third pass will start. Okay. So on. Clear? Now let's say another one here. Now check second one is. Next problem is what? The gate 2012 problem. IIT Delhi. So what is the problem here? A list of n strings, each of size n, is sorted into lexicographic order using the merge sort algorithm. Using the merge sort algorithm. The worst case running time of this computation is, option A is order of n log n, B is order of n square log n, C is order of n square plus log n, and D is order of n square. Clear? Now let's check here. What is the computation time here? What is the running time here? Okay, let's check here. So here a list of n strings. So there are n strings are there. Each of size is n. Okay, a list of n strings are there. Each of size n, sorted in lexicographic order. So lexicographic means dictionary order. So dictionary order is called lexicographic order. Okay. Using the merge sort algorithm here. So what is the running time is? What is the complexity here? Okay. So let's check here. So there are n strings are there. Okay, and each of size is n here. List of n string, each of size n here. So here n. So here n. Okay, so there are total n strings are there. Total n strings are there. Each of size is n here. Okay. So for one list of length n, how much time it will take through the merge sort? Okay, for one list, for list of n element, how much time it will take order of n log n time required? For list of n elements, how much time it will require order of n log n time required? But here how many strings are there? N strings are there. So one list will take n log n time. Then there are n lists are there. So how much time it will take? N into n log n. So how much here? N square log n time is there. N square log n time is there. So what is the answer here? B for Bombay is the answer. So one list time complexity is order of log n log n here. So there are n lists are there. Then n into n log n are there. So n square log n here. N square log n here. So this is the answer. N square log n is the answer here. Clear? So this is one of the gate problem here. So these type of problems are very common here. So very good problems are there here. And let's check another one. So next one is what? So here consider the following functions. Consider the following functions. So here fn is what here? N factorial. Gn is e raised to power n. H of n is root 2 log n. K of n is 2 raised to power n, and ln is here n cube is there. Okay. So which one is it true here? Which one is it true here? So this is the order is given like that. Fn less than Hn less than Gn less than Kn less than Ln. B is Fn less than Ln less than Kn less than Gn less than Hn. C is Hn less than Ln less than Gn less than Kn less than Fn. D is h of n less than ln less than kn less than gn less than fn. Okay, so let's check here which one is correct. Okay, which one is correct here? So here fn is what here? Big of n raised to power n. So it's a bigger function here. So exponential function growth rate is, so what is the note here? So you know very well, exponential function growth rate is higher than any polynomial except this one. So exponential function rate is higher than any polynomial except n raised to power n. Except n raised to power n here. So it having higher growth rate, okay, always. So this is a very bigger function here. So fn is here. So let's check here. Let's see here. So here fn, okay. So here ln there. So a is wrong here, b is wrong here. So try to eliminate the function here. So hn and hn, ln and hn go on because fn growth is higher than any of the function. So a and b are eliminated here. So a and b are the eliminated here. So eliminate this one. Okay, this one here. So now c and d are remaining here. So let's check here. C and D are remaining. Okay. So Fn, first one is Fn, no problem here. Now Gn. Okay. So E value is 2.71. So it becomes 2.7 raised to power n here. And here is it e raised to power n here. So okay. Here 2 raised to power n here. So Gn is bigger than Kn. Okay. Gn is bigger than Kn. So first of all is n raised to power n is e raised to power n. After that Kn will become 2 raised to power n here. 2 raised to power n here. After that ln. So ln what is n cube here? Okay, yeah, n cube here. So polynomial function is there and this is the constant function are there. Okay, this one. So this is the order here. So here this is what hn less than ln less than kn less than gn less than fn. So this is the order. So what order में here D is, so D is the correct answer. So D is the correct answer. So this function growth rate is a very higher than any polynomial. Any polynomial here. Okay. So n raised to power n growth rate is higher than any polynomial. Clear? This one is okay. So this is the good problem here. So let's take another one. Take another one here. So next problem. So we will discuss more of the problems in the next upcoming lecture. So these are the some problems is based on the merge sort algorithm. So in next part we will discuss more of the merge sort problems, the how the merge sort works here. Very standard problems, very advanced problem here. Okay, thank you everyone.